All right, let's talk one last time about these languages and such. Last time, in my opinion, was quite abstract. I want to talk a little bit more down-to-earth terms about what all of this stuff means in terms of the halting problem and recursive and RE and non-recursive, non-RE, that kind of stuff. Anyway, I will just start with this same old diagram here. The regular languages, the context-free. So this category called recursive, this includes ordinary looking languages like A to the N, B to the N, C to the N. So that language is in this category. What that means is you can't make that language with a context-free grammar, but you can with a Turing machine. And this should be unsurprising to everybody. I mean, if you think of a Turing machine's capabilities are basically the same as a real-life computer. And so certainly a real-life computer is capable of deciding if a string looks like this or not. And so that puts it in the category of recursive. This means, remember, the language of a total Turing machine. That is the language of a Turing machine which never has any infinite loops. And you can make something like A to the N, B to the N, C to the N out of that. In fact, you can get any amount of A to the N, B to the N, C to the N, D to the N, or whatever. All right. Then the next category out are called RE, that is recursively enumerable. And these ones can be accepted by a Turing machine, but that Turing machine may have infinite loops on the non-accepted strings. And this includes what I called last time LH, that is the language of the halting problem. And I will just very briefly refresh our memory. The language of the halting problem is strings that look like something like M together with X, where M describes a Turing machine. So this such that M is a Turing machine which halts on X. All right. And what we talked about last time, like why is it in this RE category but not the recursive category? What that means is apparently you can do this on a Turing machine, but not a Turing machine which has no infinite loops. So the reason that this is in that category, we did a more technical proof last time, but what it means basically is, I'll just say LH is RE, but not recursive, since it's possible. The question, creating this language is all about, can you make up a machine which decides if you have some other Turing machine, can you decide if that other machine will halt on X or not, right? And it's RE but not recursive, since it is possible to check when M halts on X. That is, you can just run M as a Turing machine on X, and it will halt. You can verify that using another Turing machine. But you cannot do the more complicated question of, so I will say, but we can't tell whether or not M halts on X. This is a very subtle difference, since this may cause infinite loops. All right. So, can you see the subtle difference? It is possible to check when something halts, but it is not possible to tell whether or not it halts. All right. So if you know ahead of time that it's going to stop, then you can verify that it will stop by just running the Turing machine, and when it stops, you know that it stopped. But you cannot just take a string out of nowhere and ask the question, is it going to stop or not? That is not possible to answer, because you can't tell, in practice, you can't tell the difference between something which is running for a long time but may eventually stop versus something which is an infinite loop. All right. And that's what this, like being in this category over here, this RE but not recursive, it means these are languages where you can't tell whether or not a string is in that language. But if somebody shows you that it is, then you can verify that it is. All right? This is a little strange, but I'm going to write something like that. So this is not about the halting problem anymore, but just generally speaking, if L is RE, this is some other language in general, RE but not recursive, that means, I'll say then, there exists an algorithm. By algorithm, I mean just like a procedure to decide something. In more technical sense, it's a Turing machine that can make that decision. But anyway, there exists an algorithm to verify that X is in L, but there does not exist an algorithm to tell whether or not X is in L. This is the subtle distinction, all right? And this is true of the halting problem. It is possible to verify that a certain Turing machine will halt on a certain input, but it is not possible in general to decide whether or not it's going to halt. Because the second one, you are in this situation when you can't tell the difference between an infinite loop and something which is just taking a long time to decide, all right? This is the character of any language. This is not just true of the halting problem, but any language in this category, that is in the RE but not recursive. That's what it means, all right? This is a very subtle difference between verifying that something is true versus saying yes or no, is it true or not? Those are very different questions, all right? This, I don't know if anybody is into this stuff, but this is actually, what I'm saying here, I don't want to get into it really, but this is very closely related to what they call the P versus NP problem, which is, maybe you've heard of. This is generally regarded as the most important unsolved problem in computer science today. So if you ever want to, there's a $1 million prize associated to this problem too. So if you're looking for a quick buck, you can try to prove the P versus NP conjecture. I would not recommend it, actually. There are better ways to make a living. But yeah, very, very subtle ideas and very important in terms of like what people, you know, in the field today think is important. So I want to say one more thing about this diagram here. I promised last time that we would discuss something outside here. That would be something which cannot even be decided by any Turing machine, even if you allow it to run sort of like for an infinite amount of time. And that we can find languages like that. I have just one last theorem for our semester. It says, and this is not very complicated, if L is RE but not recursive, that means it's in that category that I've been talking about here. RE but not recursive. This means it is possible to verify that something is in L, but it's not possible to decide whether or not something is in L, right? If L is RE but not recursive, then L bar is not RE. That means in the universe of languages, it's outside that largest circle that I drew, right? It's not even RE at all right? L bar meaning the complement, of course. This means complement. All right. And here's why. This is not very complicated. So the argument is going to be by a contradiction. So to get a contradiction, we would assume that L bar is RE, right? And what that means, so there exists an algorithm to verify if X is in L bar, right? i.e., this of course means X is not in L. So there is an algorithm to verify, not decide yes or no, but to verify that X is not in L, all right? But since we assumed, what did we assume? The assumption of the theorem is that L is RE but not recursive. So I'm going to say since L is RE but not recursive. We know, because of what I said before, there exists an algorithm to verify if X is in L, right? But not to tell one or the other. So there exists an algorithm to verify if X is in L, but no algorithm to decide whether or not X is in L. All right? But the contradiction, this is a contradiction, right? Is right here. I said there exists an algorithm to verify if X is not in L, and we also said there exists an algorithm to verify if X is in L. That means if you just run the two algorithms at the same time, you have a procedure to decide whether or not X is in L. And that's the contradiction with right here. I just said there's no algorithm to decide whether or not X is in L. So I will just say, do these together. These meaning this one and this one. We have an algorithm to decide, to verify that X is not in L, and also an algorithm to verify that X is in L. And that means you can actually decide yes or no, is X in the language. So do these together, and there is an algorithm to decide whether or not X is in L. All right, and this is a contradiction. Contradicts the thing I underlined in blue. And you may notice that I never learned properly how to spell the word whether. Sometimes I put the H, sometimes I don't. That's just how I do it. It should have the H, right? Yes, okay. You can insert the H as you like. I will not take off points if you leave the H out. All right. So this is the last theorem that I wanted to talk about. The conclusion is, remember, if L is RE but not recursive, then L bar is not RE. And that means on our big diagram up here, what's an example of something outside here? Something which is not, not RE. Anybody say? Yeah? The complement of this one, LH, right? Anything in this category, its complement will be out here. So if you want a specific example, you can take the complement of LH. There you go. This is the complement of the language of the halting problem. So this would consist of strings which do not look like this, M hashtag X, where M is a Turing machine that halts on X. This, in my opinion, is very, very weird language, and I have a hard time thinking about what that even means. I mean, I know what it means, but it's very weird. It's all strings except for these ones. And that is not even in the RE. That means there's not even a Turing machine which, if you already know that it's accepted, if you already know that a string is part of this language, there's not even a Turing machine which can just verify that fact for you. And certainly, there is no Turing machine which can tell whether or not a given string is part of this language. All right? Strange but true facts. All right, I don't know if you are truly interested in that as a little conclusion to this, the picture of this diagram here, but I wanted to say, in our remaining time together, which is like another 40 minutes or so, I do have a few things to say about the final exam, which I'll leave till the end, but I wanted to talk a little bit, see how far we can get with this, in a little more sort of ordinary, down-to-earth terms about what this all means, in my opinion. So these are very abstract, but my sort of interpretation, or the big takeaway that I would like for you all to bring home with you after this course is over, you can tell your moms about it when you go home for break. The big takeaway, in my opinion, what's interesting about all this, even if you don't want to get into the details, I would say there are some problems or questions, such as, does this Turing machine halt when I use this input? There are some questions that are simply beyond the capabilities of any algorithm. And when I say any algorithm, I mean i.e. any computer. All right? This is what, I said this on the first day of class, there are certain things that computers are simply incapable of doing. And I don't mean things like, can a robot ever truly love? I mean, like real specific mathematical things that computers cannot do. For example, they can't solve the halting problem. Now, when you get to that point in your conversation with your grandma, she might not know what you're talking about, but at least you can say, trust me, grandma, there actually are real mathematical questions that cannot be answered by any computer. This may affect, I don't know, how you feel about AI. Like I myself, I hope you don't mind if I share a little bit of my own personal opinion on some of these matters. I myself am kind of a true believer in AI. Like not in terms of like our current capabilities, but I kind of do think that in the deep future we will have computers that are basically the same as people in terms of their intellectual, emotional existence or something like that. I kind of do think that will happen someday. Those computers, though, still will not be able to solve the halting problem unless there is some kind of, unless they're not based on the laws of physics as we currently understand them. You might feel like, oh, if we don't know how to solve the halting problem, maybe we should just like work harder on that and figure it out. And the answer is, it's not like that. This is like a mathematical limitation. It's not just like a technological thing. I would say if you're trying to solve the halting problem, you should not be trying to build a new kind of computer. You should be like building a particle accelerator or something. Like you need to discover new laws of physics rather than just new ideas, right? Anyway, this makes me think interesting thoughts. I don't know if you've ever thought about this. I said i.e. any computer, but what about, anybody want to guess what I'm about to say? What about people? The folks. When I say no computer can solve the halting problem, this immediately makes me think about myself and like the halting problem in the sense of, can you tell whether something is going to have an infinite loop or not? I don't know, do most people think that you could do that even though a computer can't? I sort of, you have to ask yourself, is me as a person, like the whatever mechanism I'm using to think and decide, figure out, solve problems, am I doing something that in principle a Turing machine can do, or is there something about my brain which is operating not like a Turing machine? I would say these are things for everybody to think about, and I don't want to give away all the answers. Anybody have any opinions about this? The question of like, are people just like Turing machines, or is there something sort of extra special deep down inside of us that makes us different? You got an opinion?
You might be better at being able to be like that strict, most likely will cause a problem, but like that's easily like will get out of control with a bigger string.
Yeah, right. Yeah, so I think if I give you like a piece of Python code and ask you, hey, is this going to have an infinite loop or not? If it's printed out on one piece of paper, you could probably look through it and figure it out. But if it's some giant thing, you're not going to be able to tell if it's going to halt or not. I think there is kind of a knee-jerk illusion that this is something that maybe human beings are better at than computers, although I think that's only really the case for small examples. Anybody have other opinions about this? Yeah?
I think that it's like technically like impossible to prove because it's an infinite loop, which means that it's like infinity, so it's impossible to tell whether it'll go forever. And like I think that the reasons computers can't do it is because computers operate kind of like they only give you like a solid answer rather than like a probable answer. And I think that like for infinite loops, like humans can give probable answers saying it's probably an infinite loop, but
All right. Yeah. Maybe we could put the desks in a circle and have a deep discussion about this? I don't know. I'm not actually suggesting that. These are things I would encourage you to think about. In my opinion, they're very interesting questions. I don't know if you all think the same things are interesting as I do, but these are interesting questions. I kind of feel like if human beings have some kind of ability to reason in kind of a probabilistic sense, do you think we could teach a computer to do that too? I don't know. I think, the question, a big question that this comes down to is something like, is a brain equivalent to a Turing machine, right? And this is something that, of course, nobody really knows the answer to this for sure. Although my own personal opinion is, I think probably the answer is yes. I feel like a human brain, has something like a tape, like all the, I don't know, my memory. I don't know how memory works. It has to work somehow. Like it does work by some physical method, right? Like I do believe like my brain is a physical object that, is not. I don't think that a human brain is like a magical thing. It's an amazing thing for sure, but it's I think there is a mechanism or a method by which it works, and because of that, I feel like it probably is the same as a Turing machine. I don't know. Anybody have any thoughts about that?
If someone went back in time like 5 seconds, I think that everyone would continue to do the same thing. So it's like not based on like luck or randomness. Which I guess would make sense if it was a Turing machine.
So I think if you believe that, then probably the brain is something like a Turing machine. And there's like this. I can remember thinking about this when I was a young lad, and I thought like, man, if in a sense it's like, well, if we're all like robots, then like, what's the point of anything? What's the point of like being a good person if it's just like, whatever? I'm not, You can wonder about questions about like free will or whatever. And it also this can be interpreted as being very kind of dismissive of human beings as people. So I really do believe that people are sort of have moral value, and I think that if you want to get really personal about it, I believe that people are like children of God, and I think there is a real value to every person in a way that I don't think like my phone has the same kind of value as each of you, right? I would not throw you against the wall. I wouldn't throw my phone against the wall, but I wouldn't feel badly about it necessarily if I did, And so, for me to say, I kind of do think that people are basically Turing machines. I'm not saying that they are of the same worth as a calculator, but it is it's an uncomfortable idea. Anybody have any thoughts about that? By the way, I hope you don't mind me sharing my own opinion. You are totally free to disagree with me. These are not mathematical things that I'm saying at this point. I kind of believe the answer to this question is yes, but these are things. But anyway, if so, that means these limitations of Turing machines are all also limitations of human beings. These are also limitations of people, right? Now, just because I kind of opened a door for this, I said the G word a few minutes ago. This is a little something to think about. What about God? I don't care for the next few minutes, at least, if you believe in God or not. But I'm just thinking, sort of hypothetically speaking, does it even make sense that there could be some kind of intelligence which knows everything or something like that? Because I would say, if God is real, God is not a Turing machine, because God is not supposed to have limitations like this. Unless you could say God is real and God has these kinds of limitations, although that's not the typical picture of what people usually mean when they say God.
So would God be like the L bars?
The L bar? Yeah, it's God like out.
That is the complement of the halting problem.
God is out here. Somehow, like I feel like if God is real in the way that, most people when they say God, they mean some kind of something which knows everything and can answer every question. And so that means, I would say, the interpretation of that, so if you do believe in God, and if you do believe that God can answer any question, I think what that must mean is that God, in God's reasoning, God does not function like a Turing machine at all. And I would say, to me, what that means is God doesn't actually reason in the sense that we would say. Like when I try to solve a problem, I work it through step by step to arrive at an answer. But this is not the way, apparently, this is not the way that God figures stuff out, because that is the way that a Turing machine figures stuff out. But if something is operating on a different level, then it's not like that. These are weird things to think about. Any other thoughts about this? So I have heard some people say this means that God can't exist, because anything that thinks has limitations in terms of what kinds of questions that they can answer, according to this business here. Now you would say, and I mentioned this before, but here this shows that there are certain types of weird halting type questions that Turing machines can't answer. You could imagine a larger category. Maybe God exists in some kind of larger category. But actually, it is a true fact that any category which you can produce, it is possible to find languages that fall outside of that category in terms of their computation. This is what I said before about, like, you can add a halting oracle into a Turing machine, but that doesn't make it able to answer all questions. It just it pushes the boundaries back, but there will still be questions that can't be answered in that sense. Interesting thoughts. I'm just trying to give you some things to think about. Talk to your stoner friends about it. And they'll be like, yeah, I think these are interesting questions. One thing, though, that this means, and this is something that I, as a mathematician, care deeply about, so forget about God for the moment. What this means, absolutely for sure, it means that some mathematical questions are sort of permanently unanswerable by people, at least, or by Turing machines. If you think that people are somehow magical, then maybe they could answer these, but that are permanently unanswerable. All right? And this, just as a person who does math for a living, this is an interesting thing to me. And this also, I have heard people have different opinions about. Some people, when they learn this, view it as somehow extremely bad news. It is a great limitation of the whole concept of mathematical endeavor. If you think that mathematics is all about figuring out everything, what this means is that this is a doomed enterprise. It is not possible to figure out everything. My own impression of that, like, to me, this is good news. This is very good news, in my opinion. It means that mathematics, the endeavor of mathematics, will live forever. There is no end of mathematics, in a way that I feel like, at least, I mean, this is somewhat controversial, but at least it seems possible to me that there could be an end to physics. Like, there are laws of the universe, and at some point, we may just discover all of the laws, and that's it. This is more or less what people thought had happened after Isaac Newton. They had figured out everything. And that is certainly possible that will happen in our understanding of the universe. But that cannot happen in mathematics, because there is no, there are some questions which can never be answered, and we can continually get closer and closer, but not find the answers. Anybody have any feelings about this? A lot of times when I talk to people, when I meet people, in the club or whatever, a lot of people tell me, like, oh, I really liked math when I was a kid, but then, I had a bad teacher or whatever, they don't like it anymore. But one thing people tell me is, what I like about math is that every question always has an answer. And you might not know how to get there, but I have some kind of a good feeling in my heart to know that there always is an answer. And if I can just figure it out, I'll make it. And to these people, I usually say, right on. But deep down inside, what I'm thinking is, this person is wrong. This is not actually true of mathematics. This is true of everything that a kid learns, in math. But this is not actually the true nature of mathematics. There are deep questions which cannot be answered, and I like that. Any more thoughts about all this? These are things that I know I'm just sort of saying a lot of stuff, but I hope that this sounds interesting to folks. Yeah.
So the question's slightly unrelated. If you can prove one of the $1 million questions to be unanswerable, do you still get $1 million?
Yeah, that's a valid conclusion. Yeah.
Okay.
Yeah, and that's, if you talk to people who are really working hard on these problems, that's something that everybody thinks about as a possible resolution. The problems, like right now, there are $7 million problems that were posed in the year 2000 called the Millennium Problems, and they were inspired by a list of about 20 problems from the year 1900. That those ones did not have monetary prizes on them, but they were super influential. And of those 20, almost all of them have been solved. One of them is the Poincare conjecture, which is now one of the 7. That one still exists. But I think maybe 2 or 3 of those original 20 were actually proved to be undecidable, and so that was regarded as that's a perfectly good resolution to those kinds of questions. Yeah. So we got about 20 more minutes. I want to try and go talk about 2 specific examples that you can tell to your grandmas or whoever about mathematically unanswerable things. Now, your grandmas are likely to not want to hear about the halting problem. This is typically the first kind of basic example of this sort of thing that people talk about, but the halting problem is about other Turing machines, and it's a very weird kind of setup. Unfortunately, this first one that I want to talk about is also kind of weird, but I would like to talk about something called, it puts the same basic idea but into a slightly different context. The halting probability. The halting probability, all right? This is known by a few different names. This is sometimes called, and I'm sorry, I don't know how to pronounce this. This is a person's name, Kittin, I think. I think this is a Russian, although I kind of know how to pronounce Russian, but I don't know how this is written in Russian. Anyway, this is sometimes called Kittin's number, or constant, or something like that. This is a famous number. It is a specific number, kind of like, pi or e or whatever, but it has to do with the halting problem, and this is how you define this constant. I'm going to be a little vague about this, but Kittin's constant, it is defined as, I'll give some details here. Let's say I'm going to define this function f, which goes into 0, 1. This is the real interval 0, 1. I know you're not used to seeing me say those things, but the real numbers, all real numbers between 0 and 1. And this f of n is defined to be, we consider all possible strings. I mean strings on the ordinary alphabet, like strings you can make on your computer. Consider all strings of length n, and then count. So there are very, very many strings of length n, right? You count how many represent legal, let's do this for Python. How many of them represent legal Python programs which halt? All right. So you could imagine, say, do this for n equals 10. it means if I just spit out all possible strings of length 10 and then ask how many of those are legal Python programs that actually halt. The answer is probably almost none of them, because if you just generate a random string of characters, that almost certainly is not a legal Python program, right? But many of them are legal just by some weird coincidence. This is like the monkeys typing Shakespeare. You know, if you're actually generating these things at random, some of them will be legal Python programs. For example, if they begin with the comment sign, is it the hashtag in Python? If they begin with that, then it's going to be legal and it will halt, right? Most of them will not be legal. But anyway, you count how many represent legal Python programs which halt. This f of n, these numbers will be fairly small, like most of them are not. And then you look at the number of halting strings divided by the total number of all strings, I mean of length n. And this is called the halting probability. That is the probability that a randomly generated string will actually halt. All right? What I'm talking about right now is that this is called the halting probability for length n. All right? And this is a sequence. Let's call this like a sub n. Like a sequence from analysis, you know? A sequence of rational numbers. This is called the halting, each one is the halting problem for, the halting probability for length n. And it can be shown, I don't want to do the details of this, but using some theorems from analysis, it is a fact that this sequence an actually converges to a specific value. This converges. What that means is as you take higher and higher values of n, you consider longer and longer strings and ask what's the probability that a giant string will actually be a legal Python program which halts. That actually converges to a specific number. And this number is this Kittin's number. And it represents the probability that a randomly generated string, so this is, if you're going to try to explain this to your friends at dinner, this is the probability that, she's not going to explain to her friends at dinner. Maybe she's running out to call her friends right now. So you won't believe what I just heard. This is the probability that a random string is a legal halting Python program. All right, that's what this number represents. And I'm here to tell you, this number is very small, but not zero. All right, there is some probability that if you make a string at random, then it represents a Python program that halts. All right, this is the probability that a random string is a legal halting Python program. Here's what your grandma will be interested in, though. No algorithm can test if a program halts, right? This is what we've been talking about for the halting problem. And therefore, this doesn't follow exactly, but it is true, and I hope that you'll take my word for it. Thus, no algorithm can calculate the exact value of this number here, A. That number represents the probability that programs will halt or not, and that is not, it's not possible to measure that probability, which means no algorithm can calculate the exact value of this number. All right, so what we have here is, this is actually, it's typically called omega, a capital omega. is a real number, but this is the big takeaway you can tell to your friends. We cannot know all of its digits. There can be no method by which you can compute the digits of this number. You might be able to compute the first few digits, like I know the first digit. Here's how it starts, 0.0, etc. This is because it's very unlikely that a random string actually is a real Python code program that halts. But it's not equal to 0. At some point, you get non-zero digits in there. This is an example of a real number, but we cannot know all of its digits. This is another thing that kind of puts me in awkward situations in the club sometimes. Sometimes when people learn that I'm a mathematician and that I do mathematics research, new mathematics research involves typically like proving new theorems. People say to me, "Oh, do you discover a new number?" And my answer is like, so my gut reaction is something like, no, there aren't new numbers, like all the numbers are already known about. We are talking about other kinds of abstract ideas. And this is usually what I say to such a person. But the true fact is, there are actually numbers which are provably unknowable, like this number here. It is not possible to calculate the digits of that number by any procedure. I don't mean any known procedure. I mean actually any procedure. It is not possible to compute the numbers. This is called, this omega, there's a word for this. This is called, omega is uncomputable. And you can talk about like which real numbers are computable and which are not. You know, everybody knows like the real numbers are divided into the rationals and the irrationals. Actually, the rationals are all computable because you can compute the digits of any rational number by dividing the numerator divided by the denominator, and that there is an algorithm to do that. It's the long division procedure. But there are some irrationals, such as this, that are actually uncomputable. And in fact, if you know a little real analysis, if you don't know real analysis, this may not make sense. I will just say, actually, the set of uncomputable numbers, it's not just this omega, which is an example of an uncomputable number. There are other uncomputable numbers. Actually, the set of uncomputable numbers is dense in R. If you recall from analysis, what that means is that, well, one thing it means is between any two real numbers, there exists one of these uncomputable numbers. They are kind of like the irrationals in this sense. That means the uncomputable numbers are not, it's not just like there's one or two examples. Actually, there are infinitely many examples, and they are abundant inside the larger set of real numbers. They lie sort of everywhere in the real number line. There are uncomputables. Every number that you've ever heard of is sort of a tiny island in a sea of uncomputable numbers. Most of the real numbers are uncomputable. These are strange but true facts. Anybody have any feelings about that? I don't know. What I'm trying to say is all this sort of abstract nonsense that I've been saying about the halting problem or whatever, these are not really things that are confined to the level of purely abstract nonsense. There are actually numbers that are like this. There are numbers which you can't compute the digits of. All right? This is something I've tried to talk with people every so often and have a hard time convincing. They're like, what? How could that be? Well, it is. I mean, yeah. It's hard to convince somebody who already thinks that common sense can only get you so far in this kind of thing. There is some kind of violation of common sense, I agree, when somebody tells you there is such a thing as a number that you could never compute the digits of. They would say, how do you even know that it's real then if you can't find the digits? Well, I don't want to get into it. That's what I say. All right? I got one more example that you can tell your friends about in our remaining 5 minutes or so. This is something which the halting probability, that number, at least it still looks like something which has to do with halting. Here's an example of something which is actually appears completely innocent, but it turns out to be one of these kind of unsolvable uncomputable questions. This is called the post-correspondence problem. Correspondence problem. And you can tell your friends about this one. I'm going to call this the PCP. This was invented in 1946 by this guy named Post. Post was one of the early sort of abstract computer scientists after Turing, who was really trying to wrestle with what it means. Turing was the first one to demonstrate that there are unsolvable problems, and Post was one of the first people to kind of wrestle with that. And one of Post's goals in this post-correspondence problem was to invent an ordinary seeming question that actually turns out to be unsolvable. So it's not a question about Turing machines or about halting or about infinite loops. It seems like a totally ordinary question, but it turns out to actually be unsolvable. And here's what it is. I don't think we're not going to have time to explain what makes it, why it's not solvable. But if you are given, so it's like a little puzzle, right? If you're given blocks like this, so I will draw them like little rectangles. This was Post's invention. And the blocks, each block has a string on the top and a string on the bottom. Like this, and I got one more. All right. Each block has a string on the top and a string on the bottom. And then one of the blocks is designated as the starting block. And I'm going to, let's say the second one, I'm going to just give it a little double outline. This is the starting one. You got to start with this one. Start with this one. All right. And the post-correspondence problem, your job, this is like a little puzzle for you to solve. I give you blocks like this, and your job is to put them in some order. So you line them up in some order. You got to start with the starting block. And I will say repetitions are allowed, so you can use the same block several times if you want to. Repetitions allowed. So you want to, line them up like this, etc. And the goal here to solve the puzzle properly is that the total string that you read across the top is the same as the string across the bottom. All right. And so in this example, I must begin with this one, 1, 0, 1, 0, 1 on top and 1, 0 on the bottom. But then you can line up as many of those tiles as you like. You can repeat them if you want to. Your job is just to line them up in such a way that if you read the string across the top, it ends up being the same as if you read the string across the bottom. Anybody think you can do it in this example? You got an idea?
Is the first block next?
Oh, okay, so 0 up top, 1, 0, 1?
Yeah.
I think so. You can, if you think about this, you can kind of see where you have to go next, because this string is really long here, 1, 0, 1, 0, 1, but you know that across the bottom it must also say that, right? So across the bottom, it starts with 1, 0, but then what comes next must be 1, 0, and 1, right? Which is why I think this is why you chose that one as the next one. Okay, but this one now gives us another thing on top. Does anybody see what should go next? Yeah?
The last block.
The last block, 1 and 0, 1. And I think actually this is a complete solution. Sorry, my pen is running out. If you look across the top, it now says 1, 0, 1, 0, 1, 0, 1. And across the bottom, 1, 0, 1, 0, 1, 0, 1. Yeah. All right? So this is a good solution to this particular instance of the PCP. All right? What Post was able to demonstrate, Post showed that in general, the PCP is not solvable by a Turing machine. And the way specifically that Post did this, I was going to do the details, but we don't have time, is that he demonstrated that if you somehow had some kind of magical method of solving the PCP, that could be transformed into a method for solving the halting problem. So this is referred to as reduction to the halting problem. You have some other question and you show that somehow that question, even if it doesn't seem like it, that question is somehow equivalent to the halting problem. All right? The PCP is not solvable by any Turing machine. This to me is kind of weird because like you could make like a phone game. I don't know if, I'm sure someone has done this. You can make a game on your phone or on a computer that works like this, all right? Does that go against what I just said then? I mean, you don't have to be a brilliant programmer to make this happen in a computer, right? Can anybody say what's the disconnect then? I could make a phone app that gives you these guys, and then you like drag them down in order. Yeah.
They could visually look like that, but in coding be like different code than what that is.
I don't think. I'm not sure what you mean exactly, but I don't think that's the issue. Yeah.
Are they like already known solutions?
Right. So what I'm saying here, PCP is not solvable by any Turing machine. It means if I give you one of these puzzles and ask you to give me a solution or to just say there is no such solution, that question is not possible to answer by a Turing machine or by a human brain, in my personal opinion. That doesn't mean you can't make a phone app that's based on this little game. It just means that your app is not capable of deciding on its own whether or not these puzzles have any solution, which is what she said. So if you were really making this app for real, you would probably want to, by hand, design a bunch of specific examples that you know have solutions to give to the user. Because if you just randomly generate examples and give them to the user, there's no guarantee that they're solvable or not, and it is impossible to check if they're solvable or not. This is the point. It has to do with this repetition, right? You are allowed, I said you are allowed to repeat the tiles. Repetitions allowed, all right? This is the way in which it turns out being able to detect if these tiles will ever end up with strings that are equal is actually equivalent to being able to tell if there's going to be some kind of infinite loop or not. Yeah.
Does that mean that our brains can't be Turing machines?
Oh, because we just figured this one out?
Yeah.
No. It means this one was an easy one.
Oh.
So like, certainly in any particular example, you may be able to tell if it can be solved or not. Just like in any particular example of the halting problem, if I show you a piece of code, you might be able to tell if it halts or not. The problem is there is no general procedure which can be applied to any problem of this type that will always answer the question. Yeah. Strange but true. So this business about unsolvable questions is not just the realm of weirdo questions about halting Turing machines. There are actually things which seem to be perfectly ordinary questions, but they turn out to be unsolvable. It's true. Hopefully you never have a homework question like that. This is always like in the back of my mind as a math researcher. If I'm having a real hard time figuring something out, I was like, man, maybe this is formally undecidable. It never is, though. I'm always just wrong or something. But that's how it goes, I guess. All right, we have 3 minutes on the clock. Thank you for your thoughts and participation. I would encourage you to think about all these things and talk to your friends about them. In my opinion, they're interesting. I don't know if you agree with me. What I did in terms of the final exam, I don't have much to say about it. It's going to cover everything. I have decided that the final exam should be like half of it will be focused on the new stuff, which is Turing machines, and the other half will be kind of anything goes. And I thought to be for your benefit, I have produced a little practice test. Can you believe it? This is just a final exam that I gave a few years ago. I printed this out for you all. This also, you will find this as a PDF on the website together with my answers. The answers are not on this one. You got to go look them up. But I would encourage you, if you have the time, try and work your way through these. It says on the top there, these are sample questions. It is not meant to be exhaustive of anything that could possibly be on the test, but one more. I hope that that's helpful.
Yeah.
Does anybody have any real quick questions about the test? I think you all probably know what to expect by now. All right, I think that'll do it then. See you whenever the test is. I don't remember off the top of my head.